So in this video, we're going to talk about predicting acidity trends. So this is actually a review of chapter 2. And we're just going to take a few minutes just to quickly review this because this chapter does deal with carboxylic acids and their relative acidities. So let's try this, okay? So let's say that we have these three molecules here, right? These three molecules here. And I'm going to label these as molecules A. Oops, let's go back up here. Label these as molecules A, B, and C. Go ahead and rank these in order from most acidic to the least acidic. Go ahead and do that on your paper and then answer the question ranking these from the most acidic to the least acidic. All right, so let's go ahead and tackle how would we do this. Again, so this is Organic 1, Chapter 2. So it is a review, but let's go through the process. So because you should be expecting some pre-response questions on these exams, so there's going to be a little slot for you to be able to answer a question just by typing in an explanation, right? And one way to be able to predict these trends is that you have to draw the conjugate base for all these molecules, right? So if we put out the steps here, the first thing that we have to do is draw the conjugate bases for all of these molecules. So if we did that, we say, okay, the conjugate base for this alcohol is this negatively charged oxygen here. The conjugate base for this carboxylic acid is this here, and this is the conjugate base of phenol. All right, so that's the first step. Draw the conjugate bases for all the molecule. The next thing that we need to do is to determine conjugate base stability. All right, determine conjugate base stability. Because what we realize is that the more stable the conjugate base, the more acidic the molecule, right? Because it's not going to lose a proton unless it's stable when it does so. And if we defined an acid as a proton donor, then hopefully we can reason out, or we can understand that, or let's try this. If we know that an acid is a proton donor, can we agree that the more readily it's available to lose a proton, the better the acid? Right? The more readily available it's able to donate a proton, the better the acid, right? Absolutely, right? So with that said, it's only going to give up the proton if it's stable when it loses it, right? It's the same analogy as I give. I said, you're never going to give up money, right, to somebody unless you are stable, you can still afford to pay all your bills when you lose that money, right? So it's the same thing, right? This acid is not going to be willing to donate the proton unless it's stable when it loses the proton. And we remember from Organic 1 how to determine conjugate base stability, and that's using the acronym HIGHER, but backwards here. So we would say higher. And the first thing that we should look at is the element effect, followed by resonance, followed by inductive, followed by hybridization, right? And they are in order of their significance, element being the most important, followed by resonance, followed by inductive, followed by hybridization. And if we look at this, the element effect says we want the negative charge on the more electronegative atom, right? And it also says that we want the negative charge on the larger atom. So in this case, we want to make sure that in this case, the negative charge is on oxygen in all of the cases, right? On all of the cases. So with that said, element effect is not going to really help us that much here, right? Now, if we think about resonance, well, can resonance help us? Yeah, it has the potential to help us here. Because what we see is that between the only ones that can resonate is going to be this one here. This can resonate, and then this can also resonate. This can resonate from here and go through here and then out here so that has a lot more resonance ability. So, but the one that cannot resonate is this conjugate base. So since that is not resonance stabilized, it's one of the less stable conjugate bases, then that's going to be the weaker acid. It's going to be one of the least acidic. So we can automatically put that this is going to be the least acidic conjugate, weak acidic acid. Now, comparing these two here, if we draw out those resonance structures, right, and let me kind of do this one step at a time. So if we draw out these resonance structures, this one here, we'll put the negative charge here. All right, so there's that resonance structure. Then this one would end up here. Right? And then you imagine that we can draw another resonance structure. We end up with this. And we can draw another. We end up with this. So if we think about it, between the two, which one do you think is going to be the most stable conjugate base? Which one is going to be the most stable conjugate base? Well, hopefully you realize that it's actually going to be it's going to be the carboxylate, right? Why? Because in this case, the negative charge ends up on oxygen. Even though this one here has more resonance structures, even though it has a lot more resonance structures, it's going to have a negative charge always on a carbon, right? Always on a carbon here. So it's preferred to have the negative charge on an oxygen rather than having it on a carbon. And that is what we call the element effect. And we got to remember that in these type of reactions, the element effect is, or in these type of problems, the element effect is going to trump the resonance effect, right? It's going to trump the resonance effect. So what we'll realize is that the most acidic in this case is going to actually be B, then C, and the least acidic is A. All right, so hopefully that kind of reviewed that for chapter 2. If you don't, definitely go back to look at chapter 2 and review that. And remember that in order to get this answer right, especially when we're talking about relative acidity, to explain this, we always have to mention the conjugate base. That conjugate base. Why? Why? Because it's always about the base. It's all about that base, right? And we want to make sure that we discuss that.
I'm all about that bass,